All right, so last week we talked about the first primary analysis technique for time series type data, and that technique was seasonal decomposition. This week we're going to talk about the second of really three big techniques that we're going to talk about in this class. And the second technique that we're going to talk about is a really important, very widely used methodology referred to as exponential smoothing. So exponential smoothing, much like our earlier seasonal decomposition models, just like the models we talked about last week, started out as this kind of like intuitive, empirically based approach. Wasn't based so much on theory, but maybe more so like this was just kind of like a sensible way to handle the data. And after being utilized, it appeared that it worked, and by doing so, kind of justified its utility. But kind of interesting, right? Kind of like a pretty cool story. Maybe, who knows? Maybe the story could be the topic of a good presentation. So relatively recently, in the 2000s, this theoretical foundation referred to as state models was discovered, and this theoretical foundation kind of helped give like a grounding to exponential smoothing, and also gave it a little bit more of a rigorous foundation, which allowed a bunch of things. Perhaps most importantly, a kind of theoretically justifiable calculation of prediction intervals. Right, because again, at the end of the day, probably one of our biggest uses of our methodology, whichever method we end up using, is going to be forecasts. And of course, anytime we generate a forecast, we're going to want to know like what kind of error do we have associated with our forecast. So those prediction intervals are, of course, critically important. Now, what is exponential smoothing? What is it bringing to the table for us, right? What what's the unique feather in its cap? Um, what makes it so important? Well, remember from last week that our seasonal decomposition, and even right going back even further, right, these kind of like these 512 based approaches to linear models. Both of those approaches required the overall trend levels and the seasonal factors to remain fixed over time, right? That is, if we had a seasonal factor for January, and that seasonal factor was say 2, and maybe we're talking about a multiplicative model, so basically we're saying that every January sales are twice what we would expect them to be, right? Our previous methodology has to say that that's always the case. It's always the case that every time it's January, sales are 2 times more than expected, right? That is, that seasonality effect attributable to January does not change with time. And I don't know. I mean, for like a seasonal effect, that probably is maybe a reasonable assumption. If we're not looking at like some kind of crazy data set spanning centuries. Um, but particularly when we're looking at things like overall trends, right, it's probably less realistic. That is, if we have some linear trend, like sloping upward at, say, like a slope of 10, right, it's probably unrealistic to assume it's just going to slope upwards forever. And even more unrealistic that that trajectory is going to stay exactly the same. And so it's nice to have a methodology that allows us that extra flexibility to consider situations where this say this linear trend, for example, might be increasing or diminishing over time, reflecting, right, maybe some sort of like our products taking off, hence our slope is increasing, right, or maybe the market's starting to get saturated, so our slope is instead starting to decrease. All right, so yeah, so here we are, right? Today is the day that we will consider right, an approach, exponential smoothing, right, spoilers, that allows us to consider situations where trend parameters and seasonal factors can change over time. Exponential smoothing will do this for us. It will relax this assumption. How does it do so? Well, we're gonna not an easy answer. We're gonna spend a lot of slides looking at it, but the big picture idea is that exponential smoothing does this by weighting recent observations more than earlier observations, right? Which is, I think, very intuitive, isn't it? That is, all right, if I have say 100 time points, maybe like the most recent time points are in some way more meaningful in terms of assessing the trend today than the time points, say 100 time points back, whatever that might be, right? If we're talking about quarters, that'd be like 20 years ago. So I think exponential smoothing does have like a really strong, that's what I said earlier, right? Exponential smoothing has an incredibly strong intuitive background to it. This idea that recent observations should carry more weight than earlier observations. Right? The question becomes, and like the analytics is basically how, right, in trying to determine like optimally how much more weight. Um, there's there's a lot of different variations of exponential smoothing. We're gonna focus on like the 5 most widely used types, um, and they are simple exponential smoothing. So we would use that in a case where we don't think seasonality is present, and we think that our model is not really following a trend, right? So think of that as like a horizontal line. The second approach is Holt's trend corrected smoothing, right? So this is where we think that we have something that might be like a linear type growth, right? Either up or down, in some piecewise, potentially, right, changing fashion. And that second bullet point is assuming no seasonality. Now, if I have seasonality in my data, right, I can consider the Holt Winter additive model, right? I would do that. So an additive model, we know from last class, an additive model is the type of model I would use if I have constant seasonal variation. If instead I have increasing or decreasing seasonal variation, I would instead use a multiplicative model. And then finally, right, we have something called the dampened trend exponential smoothing model. And that's a situation where right? I have this kind of growth or reduction that is diminishing over time, that is dampening over time. All right, so we're gonna look. The formulas can get like a little bit it can get a little bit dense. It's easy to get overwhelmed by them. Our textbook has all of the formulas for those of you that I don't know, for those of you that are formula stands. Um, I'm going to just focus on the first two because the formulas get kind of increasingly crazy, as we might expect, as the models get increasingly complex. But the formulas aren't too bad in the first two situations. They're somewhat simpler, somewhat more straightforward. So let's start with this simple exponential smoothing, right? So a simple exponential smoothing, that would be the situation where you think that your underlying model is one of no trend, right? So a no trend model is essentially just like a y-intercept, right? That would be the situation where y sub t, y is our dependent variable, could be price of a stock, right? Could be population in Chicago on a certain year, um, could be temperature, is equal to some constant, beta naught, and then of course, right, it sort of fluctuates around that constant, so we have that error term. Now, in a simple situation like this, it should it should not be a surprise to us that beta naught's estimate, like in a 512 setting, and here our book uses some notation a little different than what we're used to for 512, right? In 512, we would call the estimate what? We would call the estimate beta naught hat. Our time series textbook uses some different notation. I decided to preserve their notation just to minimize confusion. Instead of putting a beta naught hat, they put a lowercase b, so b naught, I guess we might call it. Um, but like in a 512 setting, right? It should hopefully be intuitive to us that if we think we have a horizontal line and we want to estimate the y-intercept, right, which is essentially where that line is centered at, that is just going to be summing all the observations and dividing by n. It's just going to be basically the sample mean, right? If I think that population is fixed around some point, and, it has maybe a little bit of fluctuations up and down every year, but on average stays the same, right? That key idea, on average stays the same, and I want to assess what that average is, I'm going to do that by taking the sample mean. Right? So that's what I would do in kind of like the static kind of 512 environment. But what would I do instead if I think that there is this kind of like this overall average, but I think that overall average might be slowly changing over time, right? And if it's slowly changing over time, then what's that implying? What that's implying is that, right, older terms are increasingly irrelevant. Newer terms have more power, more impact, should have more weight, more heft. Yeah, so what are we going to do? So, right, if you think of that sample mean that we created, is what? It is literally adding up every observation and giving every observation the exact same weight. That is, every observation has a weight of 1 over n, where n is our sample size, right? So our estimate for beta naught, our estimate for this common mean, for this constant trend, right, is basically, say I have like 12 observations, it's basically giving every observation, all 12 observations, it's giving them all a weight of 1/12, right? It's like the most democratic process. And we do it a lot in statistics. In general, it's probably the most common thing that we do. Right? We say, okay, let's be fair about it. I have 12 observations. All of them, I have no reason to think one is in some way better than the other. So I'm just going to give them all an equal weight of 1/12. But again, right, in a time series context, right, maybe that's not necessarily the best way to approach the problem, right? In a time series context, maybe observation for time point 1 should have a weight less than 1/12. And maybe the observation for time point 12, our most recent observation, should have a weight more than 1/12. Right? So I think that's hopefully an intuitive idea. I hope it's an idea that we can buy into. And if that's the case, then the only question that now remains before us is how. How do we go about doing this? And we're going to do that with this formulaic, iterative process known as, right, simple exponential smoothing is the type of exponential smoothing we're focusing on right now. All right, so here's how the iterative process works. We start with an estimate of the time series at time 0, essentially. So it's like a seed almost, like an initial estimate. And we're going to basically use our data to like update this. Now, the initial estimate is not that important because it's going to change as we start working our way through the data. And you could start with like pretty drastically different initial estimates and still end up arriving at very close to the same sort of final conclusion. Right? So we kind of have to start with something. What we start with doesn't matter a ton. And you'll see different books have different starting points. Our book uses this starting point. It basically says, all right, my initial estimate for the constant mean at time point 0, so sort of my starting point, is I'm basically going to kind of do like what I did before. I'm just going to take like the sample mean. I'm just going to use the first half of the data, and that'll give me like a good starting point for what that like initial overall mean might have been basically before I started collecting my data, right? That's the idea of like this time point 0. It's kind of like what was this trend at before I started collecting my data. And then we're going to basically start working our way through our data, and we're going to see, like we're going to look at time point 1, time point 2, time point 3, time point 4, and how do we think this overall trend may or may not be changing. All right, so we take our initial estimate for the level, right? That's script L, right? They use that little fancy script, right? Because statistics is fancy. And right, we have the script L. Script L is our initial estimate at time point 0. And now we want to come up with an estimate for what we think that level is at time point 1, right? In 512, like I say that it's the same at time point 1 as 2 or 3, right? In like a 512 context, I just have beta naught or beta naught hat. But right here, exponential smoothing, I'm using it because I think that overall level might be changing. And if that overall level might be changing, then yeah, I want to look at it at every single time point. So if I want to see what that level is, if I want an estimate for the underlying level, right, script L1, but you can almost think of that as like beta naught at time point 1. Then what I'm going to do is I'm going to make that this linear combination of basically two things, right? So what do I have to work with? So what do I think the level is? What do I think the level is at time point 1? Well, I one possible guess is it's what I thought the level was at time point 0, right? Because I'm assuming it's a horizontal line. So based on that assumption of it being a horizontal line, right, script L0 would be especially at time 0, right? At time 0, my best guess for like what level would be at time point 1 would be L0. So I could almost think of that as like a prediction, right? Script L0 is like my prediction. It's my best guess for where I thought Y would be at time point 1. And then of course I can look at the actual value of Y1. So it's kind of like what? It's kind of like observed and predicted, right? Y1 is the observed, L0 is the predicted. And what I'm basically going to do is I'm going to weight these two values. I'm going to give Y1 a weight of alpha. I'm going to give L0 the weight of 1 minus alpha, where alpha is a weight between 0 and 1. We refer to it in the context of exponential smoothing. We refer to it as our smoothing constant. All right. Now, I'm going to put this out there for us to think about, and you can pause this if you want. Click the space bar or whatever, and think about it a little bit. It might become more apparent when you look at the formula on the next slide. If we have a situation where that overall level is changing dramatically, then alpha is going to be large. If instead we have a situation where like the level is not changing at all, that is, it's kind of like a 512 kind of problem where the mean has just stayed constant for all of time in perpetuity, then alpha is going to be small, right? So it's basically how large alpha is or isn't determines how much our data is changing or not changing, right? If the data is changing a lot, then I want to put a lot of emphasis, a lot of weight on y1, my most recent time point, and very little emphasis on my estimate, which was based on all the previous information. All right. Let's look at the other slide and see if it makes it a little bit more evident. Right, so I have like my starting point. I just keep applying this formula, right? And I keep going through this formula until I essentially go through right all of my observed time points. So more generally, right, the formula is that the level at time t is a linear combination of the actual observation at time t, so that's kind of my most recent information, and what I thought the level would be at time point t minus 1, right? So again, right, if I think that it's changing a lot, if I think that like my level's changing pretty drastically, then I want to put a lot of weight on the most recent observation. So my alpha is going to be large, and of course that means 1 minus alpha will be small. So I'm putting relatively little weight on my estimate for the level, which is based on all my previous data up to this point. And what we can see, right, kind of an interesting and hopefully intuitive idea is that this formula is implying what? This formula is implying that each observation is weighted less and less and less in an exponentially decreasing manner. Let's look at the next slide to see that. I could basically like recursively keep unraveling this formula, right? Sorry, my script-L subscript changed a little bit there. I apologize for that, but that's still just supposed to be script-L. Right, so that first equation is just the one from the previous slide. But what I want us to see is what? What I want us to see is I could apply in a recursive manner, I could apply that formula to script L of t minus 1. I could apply that formula to the level at time point t minus 1. And that's what I'm doing on the second line, right? The level at t minus 1 is just alpha times y sub t minus 1 plus 1 minus alpha times the level at t minus 2. And then in the third line, I just kind of, I group things up. And if I group things up now my equation is what? Now my equation shows that the level at time t depends upon what? The observation at time t, the observation at time t minus 1, and the estimate of the level at times t minus 2. And right, hopefully we can see that if I were to apply the formula to the level at t minus 2, right, I could keep doing this over and over and over and over again until I have this long formula that goes all the way back to that level of time 0. At that point, I have to stop. So what is that showing? That's basically showing, and I hope we can see this. If you can't, come talk to me. I'm happy to like go another 2 or 3 or 4 lines into this formula. It's hard to do on this slide because it's hard if I go one more line, it kind of runs off the page. But right? If I keep applying this formula, what do I see? I see that there's a t minus 2 term and a t minus 3 term and a t minus 4 and a t minus 5, right? That this level is in fact built on all of the previous y's. If I keep recursively unraveling the levels, if I write out what the if I expand the level at t minus 2 and then expand the level at t minus 3 and then expand the level at t minus 4 and I keep expanding, then my equation is going to have a y sub t and a y sub t minus 1 and a y sub t minus 2 and a y sub t minus 3. But what do I observe? I can look at the weights, right? Remember, these weights are fractional. So the weight of y sub t is alpha. The weight for y sub t minus 1 is alpha times 1 minus alpha, right? So that's going to be, remember, we're working with fractions. So that's going to be smaller. That's going to be less weight than what we have for y sub t. If I were to unravel the level of t minus 2 and look at the weight, this might be a fun assignment for you to try out. Maybe expand just the level at t minus 2. Maybe pause it, expand that, and see that if you were to do that, then the weight for y for time point t minus 2 is going to be 1 minus alpha squared times alpha, right? Which is even less weight than we have for y sub t minus 1. Right? The weights are going to always be decreasing, right? The weights are going to be what? It's always like alpha for y sub t, and then 1 minus alpha times alpha, then 1 minus alpha squared times alpha, then it'll be 1 minus alpha cubed times alpha, then it'll be 1 minus alpha to the 4th times alpha. And so, right, because alpha is fractional, right, this number, the result, the actual weight, is getting smaller and smaller and smaller and smaller. That is, we're giving less weight to older observations. All right, so that's how we set things up. Maybe the last sort of lingering question, the last remaining question is, all right, like how do I calculate what my alpha is, right? So alpha is some number between 0 and 1. How do I actually figure out what that number between 0 and 1 should be? And so that's where we use like a computational approach, and we let SAS handle that for us. How does SAS do that? Well, SAS basically looks at the SSE, right? We know that from 512. We're familiar with that. The sum of squared error, the sum of squared residuals. It's basically looking at what? So we have y sub t minus L sub t minus 1. That's what? That's basically the difference between observed and predicted. Right? If I only had data up until time point t minus 1, again, remember, our model is assuming a horizontal line. So if I only had data up to t minus 1, and I wanted to make a prediction for time point t, I would just predict that, right, the line stays flat. So I would predict that my prediction for time point t is going to be L sub t minus 1. So I can compare that to what actually happened, y sub t. That's the error. That's my observed minus predicted. So I basically am doing what? I'm looking at observed minus predicted squared. I have the squared errors, right? Because otherwise I have these positives and negatives that would cancel each other out. And then I sum those squared errors. And so how do I figure out what alpha is? Well, SAS will computationally figure out the optimal alpha. What is the alpha that basically makes that SSE as small as possible? Right. So a little bit similar to 512, different from 512. In 512, like when we're trying to figure out like beta naught hat, beta 1 hat, and we're minimizing the sum of squared errors in that case. It turns out because of calculus, we can like solve some like explicit formulas that right? I could write into a textbook. There are no explicit formulas for alpha, where you just have to kind of like grind through this approach that will just kind of estimate it and come up with that best guess in a non-formula based approach. Which, it's tough to do by hand, maybe impossible to do by hand, but a computer can do for us very handily. All right. Now, as we said, so I have my alpha now, and that's really what I'm solving for. And this model actually only has one parameter, right? And that parameter is I guess two parameters. We're gonna have a level at time capital T. So capital T is basically the end of our data. So I'll basically have my final estimate for the level, and I'll have my smoothing constant alpha, right? So at the end of my analysis, at the end of my simple exponential smoothing, I have two things. I have my most recent guess for the level, my estimate for level at time point capital T at the end of my data, and my smoothing constant, or estimate for my smoothing constant alpha. That smoothing constant is basically telling me how much I think the data is changing or not changing over time. If it's real close to 1, I think I have very volatile data that's changing considerably over time. If it's very close to 0, I think I have stable data. The right is the underlying patterns are very stable. They're not changing over time. All right, so let's talk about predictions. So I have these. What do I do with them? Well, again, this particular model is conjecturing that there's no trend. So my prediction for any time point in the future is just going to be the level at time t. However, right, the size of my prediction interval is going to grow the further out from time t that I try to predict, right? I have more and more uncertainty. The level at time t is still the best prediction I can do, but if I think that level is changing over time, then the farther out I go, right, the less comfortable I feel using that outdated estimate. So to summarize, first off, our point estimate, our prediction for any time of capital T plus tau, right? So tau, that's the Greek letter tau. It's representing how many time points into the future we want to predict, right? So if tau is 1, I'm predicting 1 time point into the future. If tau is 2, I'm predicting 2 time points into the future. If tau is 3, I'm predicting 3 time points into the future, right? My estimate for time t plus tau is always that L of t. It doesn't depend on tau. No matter how far out, my best prediction is just that flat level, that beta naught, right? It's essentially what we have. It's like a beta naught. However, right, as promised, the prediction interval grows the further out that we get. And so there's our formula. It's a somewhat simplified formula for the prediction interval. The prediction interval is our estimate, so it's centered at our estimate, plus or minus, right, z, if we're assuming a normal distribution, t otherwise, times some standard deviation. And then, right, maybe the most important part conceptually is what comes after that standard deviation, right? It's the square root. And if I look under that square root, I see two things, right? I see my smoothing constant alpha, and I see tau, right? Tau is how far into the future I'm predicting. And so one thing that I can hopefully see, I would not expect you to memorize this formula. When you take your test, don't write this formula on a note card. But look at that formula and see, right? See with your heart, see with your soul that that prediction interval is in fact growing the further out we go, right? That is, that margin of error is increasingly large as tau gets increasingly large. It's also going to be larger if alpha is larger. And that should hopefully make sense to us, right? Because again, the larger alpha is, remember, the more we think that trend is changing, right? The more volatile we think it is. So if I think that that underlying trend is unstable, if I think that it's changing quite rapidly, then I have more uncertainty in terms of my prediction. And sure enough, right, the prediction interval that's margin of error is a function of that alpha. The larger the alpha, the larger the margin of error, the more error I expect. All right, and then the formula I showed before is like a better one computationally. If you were to kind of just like to get a sense of like how it's building up iteratively. Sometimes textbooks present the exponential smoothing in a slightly different format. It's the same formula, okay? So it's not like two different approaches or two different formulas. You can show with some algebra that these formulas are the same. But sometimes you see the formula in what's called its error correction form. And the error correction form looks like this. It says that the level at time t is basically a linear combination of my previous estimate. So what I thought the level was, plus, right, plus some fraction of the error or the residual, right? So that y sub t minus L sub t minus 1 is what? That's the residual, that's the error. So I basically say what? I'm basically saying, all right, I thought my best guess was L sub t minus 1. I compare that to what actually happened. I compare that to y sub t. I see how much I was wrong by. I see what the error was in my prediction. And that alpha is what? That alpha is basically how much I correct for that error, right? If that alpha is 0, I'm not doing any correction, right? If that alpha is 0, that's basically saying, like, I don't think that this thing is changing, so I'm just going to stay the course. On the flip side, if that alpha was, say, 1, right, that's the other extreme, it's basically saying, okay, right, let's move it all the way up to y sub t. Right? I was off by 5, so let's shift it up 5. Now, of course, typically alpha is going to be somewhere between 0 and 1. If it's close to 0, we're saying that, like, don't necessarily pay too much attention to this error, right? It's just underlying noise. If alpha is close to 1, we say, right, pay a lot of attention to this error, because this error is not noise, it's in some way informative. It's giving me some insight into how the actual level is changing over time. So this is an alternative way of expressing the formula that for some people is maybe a little bit more intuitive in terms of what's going on and how it's working. Right? So again, maybe pause it, look at that, maybe contemplate that formula for a little bit, right? And think about this idea of like how that formula is kind of like looking at an error and correcting for it. Whew! All right. What did I say? Oh man, how many exponential smoothings did I say there was? 5? Aye. Well, check. Right, we checked one of them off our list. Here's the second one. It's a little bit more complicated, but we've also laid some groundwork, so that groundwork maybe will make this a little bit easier on the flip side. This is the only one that we're going to go into in depth, and then we'll kind of hand wave the other 3. And then we'll start looking at how we might do this in SAS. We'll start looking at some actual data and some actual output. So we would use the Holtz trend-corrected exponential smoothing. We use that anytime we think that our underlying trend is a linear trend, right? That is, we think that we have y sub t is equal to beta naught plus beta 1 times t, right, with some sort of error term. And we think that the level at time t, that level we're going to think of as like a combination of beta naught and beta 1. So the level at time t is basically right where we think it's at. And we think that it's a product of some linear function or some linear formula. So the level at time t is going to be beta naught plus beta 1 times t, right? So the level at time 10 is going to be beta naught plus beta 1 times 10. So that's one thing, that's one piece we're going to look at. We have the level. We also have the growth rate, and we're allowing for the possibility that that growth rate is perhaps changing over time. That is, beta 1 is changing. All right, so these two things are potentially changing over time, the level and the growth rate. And if this is true, if in fact our underlying dynamic, if in fact the underlying mechanism is changing over time, that means that older terms are increasingly irrelevant. Again, we in 512 we didn't really highlight the formulas for beta naught hat and beta 1 hat, but the 512 formulas do weight every observation equally when calculating them. In a time series context, weighting them equally is perhaps not appropriate. So what do? It's the same process, right? Same big picture process. I'm going to go ahead and walk us through it. We have to start with initial estimates. So now, right, we're estimating two things. We're estimating level and growth rate. So we have to come up with initial estimates for both of these. And what we typically do is again, the starting point is not that important. The sort of seed. Different seeds will still probably take us to the same end point. It's the end point that matters, but we do have to start somewhere. So we need a rule of thumb. Our textbook's rule of thumb is kind of similar to what it was last time. It says run a regression on the first half of your data. Your estimate for time 0 will be basically beta naught. Right? Beta naught's the y-intercept, what I think y is at time point 0, so that makes sense. And then our growth rate at time 0 is going to be the slope of our regression equation, right? So we run like a quick proc reg on the first half of the data, and then our estimate for the level is going to be beta naught hat. Our estimate for the growth rate is going to be beta 1 hat. All right, and just like before, I update them. Now, notice I have two things that I'm updating, and I want to allow for the possibility that they're growing at different rates. And so, ideally, I want to use two different smoothing constants. All right, so I have an update for the level, and I have an update for the growth rate. The update for the level is I say, okay, my estimate for where I thought the level would be at time point 1 is my estimate for the level at time 0, and this is a linear growth rate, so I just add the slope, right? So that rightmost piece is kind of like what? That's my prediction. That's where I sort of predicted the level to be, and then y sub t is where the level actually is. Right? And I look at that linear combination, alpha times y1 plus 1 minus alpha times that estimate. And then, right, I now have to update the growth rate. So the update for the growth rate, I look at my previous estimate for the growth rate, which was B0, and I have an updated estimate for the growth rate. And the updated estimate of the growth rate is basically what? Right, remember, the slope is what? The slope is change in y over change in x. Here, our change in x, well, our change in x is a change in time. And here, our change in time is just one time point. So it's basically a new estimate of slope. It's what the level was at time 1 minus what we thought the level would be at time 0, right, divided by 1, because we just incremented 1 unit. That's our 1 unit change in y. And then I used, right, I need some other mathematical symbol, so I'm going to use the Greek letter gamma. That's what our textbook uses. So gamma times our updated estimate for the growth rate plus 1 minus gamma times our old estimate of the growth rate. Okay. More generally, I have this, right? So again, just like before, right? I'm basically looking at this, the way the exponential smoothing is going, is it's looking at two different things. It's looking at, right, if we're talking about the level, it's looking at y sub t. That's our most recent information. And then it's looking at, right, our estimate based on all the previous information. And that alpha and that 1 minus alpha is essentially the balancing act. How much weight should I put on the most recent observation, and the remaining weight, right, 1 minus alpha, is going to be distributed amongst all the previous observations. Okay. And similarly with the growth rate, I'm looking at my most recent estimate for the growth rate, right? The y sub t is not explicitly there, but remember, we're using the estimate L sub t, and L sub t has y sub t in it. So the first part of that growth rate, the first part of the b sub t equation, has y sub t in it. So I'm looking at, right, my estimate for my most recent estimate for the growth rate based on, right, my most recent observation. That's going to get some amount of weight gamma. The remaining weight is going to be distributed amongst all the previous observations. And just like before, I could recursively untangle this to see explicitly that I am literally assigning weights to every value of y, and that the amount of weights that's being assigned, the coefficient, is getting smaller and smaller and smaller and smaller, is dwindling. And it's dwindling more if alpha is larger. That is, just like before, alpha and gamma being large is essentially saying I should give more weight to most recent observations, which is implying that the underlying relationship in my data is changing over time. Okay. Just like before, I come up with an estimate for time point t. My estimate for time point t, right, based on everything up to t minus 1, is the level at time t minus 1 plus the growth rate. I compare that estimate, that y hat, to what actually happens at y. That gives me my residual. SAS then knows how to take that equation, right? It looks at the difference between observed and predicted, looks at the squared difference so that the pluses and minuses don't cancel, sums up all those squared differences, and then SAS calculates the alpha and the gamma that makes that quantity, that makes that sum as small as it could possibly be. And that's how SAS solves for it, right? So now what do we have? We have, at the end of our analysis, we're now going to have 4 different things. We're going to have an estimate for the level at our most recent time point, right? So maybe imagine that we have 50 observations. Then what we're going to actually end up with at the end of our analysis, we're going to have an estimate for the level at time point 50. We're going to have an estimate for the growth rate at time point 50. We're going to have an estimate for alpha, the smoothing constant, that tells us how much we think the level is changing over time. And we're going to have an estimate for gamma, which tells us how much we think the growth rate is changing over time. All right, so how do we use all this information? Well, if I want to do a prediction, tau time points into the future from time t is, right, the last time point in our data set. So again, imagine like time point 50. Then we have y hat, t plus tau, is what the level was at capital T plus tau times the growth rate, right? So imagine that capital T is 50, like I said before, we have 50 observations. I want to say maybe make an estimate for time point 53. Then to get that, I would look at the level at time point 50, and I would add to that 3 times the growth rate, right? That should hopefully be pretty straightforward. Here's our prediction interval. Again, I don't expect you to memorize this or anything like that. I want us to just kind of look inside that square root, and what do we see inside that square root, right? That square root is a function of, it's a function of alpha, it's a function of gamma, right? As alpha is larger, as gamma is larger, the margin of error is going to be larger. That should be intuitive. And right, it's a little bit hidden, but it's also a function of tau, right? Because I'm basically creating a sum in there, and how many things I'm adding up is a function of tau, right? So there's more parts to that sum, the larger tau is. So again, the further out I'm predicting, the larger the margin of error for my prediction interval. And again, I think this one's maybe there is some intuition there. I'll let you look at it. We also have an error correction form. We can write that iterative process before. Again, it's just like an algebraic reshuffling. We can write the formula for updating the level and updating the growth rate in this error correction form, right? And it is a function, right? Each of them has like the old estimate, L sub t minus 1 or B sub t minus 1 on the left. And then on the right is the error. The error is what? The error is the actual observation y sub t minus our best guess for what it would be, where that guess is generated at time t minus 1. Right? That's our error. All right. So there you go. Check. Right? I mean, the formulas get increasingly crazy. The formulas get increasingly cumbersome, but it's basically just the same process. As we get to more complicated models. So say I wanted to add some seasonality to my model. That is, I think there's a repetitive seasonal pattern. Maybe some linear growth with some seasonality. And I think that, I mean, I would only use an additive model in a case where I thought there's constant seasonal variation. So our model would look like what? Our model would look something like y sub t is equal to, right, I have an underlying linear trend plus a seasonal component plus, right, last class we called that the irregular term. In this context, we tend to like use that e or that epsilon to indicate like an error. And here we're allowing the level at time t, the growth rate at time t, and the seasonal factor at time t. So now I have 3 things that might be changing over time. And so I'm going to, right, if I were to show the equations, I would now have 3 equations showing how all 3 of these things are a function of previous versions of themselves, right? I would have these iterative formulas for all 3 of these things, and I would have 3 smoothing constants. Yeah. So the process is essentially analogous. I'm not going to keep walking us through it. If you want to kind of take a little deep dive yourself, our textbook does in fact walk you through it, and you can see all the iterative equations. It's the same basic big picture idea. It's just we have 3 of these things now, and because we have 3 of them, we now have a 3rd smoothing constant, which basically tells us how much the seasonal patterns are changing or not changing over time, right? The larger that seasonal smoothing constant is, the more volatile or right, the more rapidly we think that seasonal pattern is changing or fluctuating. The whole Winter's multiplicative method, is basically the same as the additive model. It's just, instead of adding these terms, we're going to be multiplying these terms. We would use the multiplicative method anytime when we look at our scatter plot and we think that we see increasing or decreasing seasonal variation. Yeah, right. So I just pasted that from the other thing. So here I have, I use the irregular term instead of the epsilon. They're representing the same thing, right? Just this kind of underlying unaccounted for error. And then finally, right, the fifth thing that we talked about, the damped trend smoothing model. This model allows us to reflect an increasingly slowed or dampened growth decline process. Right, we can also put seasonality on top of this if we wanted to, as we can combine it with some of those seasonal models. Right, and these typically are more realistic. I would actually tend to use a damped trend smoothing model, maybe over a linear model, just because, right, again, it's unrealistic that something's going to grow or shrink at the exact same rate, right, into infinity. Right, so examples might include like the number of people who have watched a new TV show. Right, we would expect maybe a lot over time, but at some point it starts to saturate. Right, at some point everyone who's going to watch it has watched it. Same with like sales of a new product. The damp trend model is really great in situations that appear to alternate between linear trends and lack of trend. And we'll look at an example of this pretty soon. It basically works by multiplying the linear growth factor by an ever decreasing fractional number. Yeah, right. So something like this. So basically, if I'm applying like the dampened trend model to like a prediction, like what's basically happening, right? The previous linear model would say if I want to predict tau time points out, say like 5 time points out, I would do L sub t plus 5 times B sub t. This is basically saying like, no, right? You have this weight. Oh man, I forgot to do my Greek letter homework. I don't know. My brain's telling me psi, but I may or may not be right about that. It's one of the more obscure ones. We'll call it psi. I don't know. We can call it. We can call it circle slash. that way I'm not necessarily wrong. I'm probably also not necessarily right. Um, but basically, it's right. It's I don't know, let's just call the weight A. So we have L sub t plus A times B, and then A squared. Now remember, this weight A is fractional, so A squared is going to be less than A. So right, instead of going up by just B sub t every time point, I'm going up by some fraction of B sub t every time point. And that fraction is getting smaller and smaller and smaller and smaller, right? How many terms? So, right, here's like a concept question for you. I want you to maybe pause and think about after I ask it. How many terms are inside that sum? How many numbers are being added together? I put a little dot, dot, dot there. How many terms are being added together? Exactly. We can actually see it by looking at that superscript, right? The last term is circle slash to the power of tau. So there's tau time points. So I mean, again, the undampened model is just b plus b plus b tau times. This is right the weight times b, the weight squared times b, the weight cubed times b, right? It's these b's in a diminishing or dampened manner. All right, so step back, summarize, right? More generally, we can consider no trend, linear trend, damped linear trend, or exponential trends. We can, on top of that, consider no seasonal variation, constant seasonal variation, and increasing, decreasing seasonal variation. And we can combine, right, these things. We can mix and match, right? Yeah, we can create exponential smoothing for any combination of these trends, seasonality. How do we choose between them? How do we choose between them? Anytime there is increasing or decreasing trend, we almost always use multiplicative seasonality. Anytime there's no increasing or decreasing seasonal trend, we tend to use additive seasonality, right? We're aware of these rule of thumbs. When it looks like we have a mix of linear and no trend, and we'll see an example of this coming up, then we try to use a damped trend model. All right. So that's like that's the theory. Now I want to kind of look at some kind of examples and some actual numbers and graphs and write something a little bit more concrete. Start with the simulation. So if you wanted to, now's maybe a good time to take a break if you haven't taken one already. Maybe pause the slide, go use the restroom. In class, this is probably where I'd be telling everyone to be taking a 10-minute break. Welcome back from your break. So I'm going to generate like a simulation data set. Again, when you're trying to play around and understand like a statistical technique, one of the most powerful ways to do that is to simulate data and see what happens, right? So here I'm simulating a data set, and what does my data set look like? My data set has time points 1 through 36. So I'm not going to use seasonality in this thing, but we could think of that as maybe like 3 years of monthly data. And apparently it's sales, right? Because that's what I named my Y variable. So these are sales. And in my simulated data, the sales have a clear linear trend, right? My beta naught is 100. My beta 1, my growth rate is 20. That third term is essentially my error term. So when I say normal -1, that's just a seed. So it's going to be a normal distribution, a standard normal, and I multiply it by 5 to just change that variation so it's not 1. Okay. And then I did a proc print just to make sure that I did it correctly, and then I did a plot of it. So I plotted, right? I plotted sales by time, which I believe is going to be the next slide. Right? So y-intercept of 100, slope of 20, 36 observations. Okay. And look, there it is, right? So what was our y-intercept? Our y-intercept was 100, so that looks right. And then it goes up, 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 up. Right, I only went up to 36, but the plot decided SAS kind of likes even numbers, I guess. So SAS went out to 40, and sure enough, if I go out to 40, what would be 40 times 20? Right, our slope was 20. So if I go out 40 points, I expect to go up 40 times 20. 40 times 20 is 800, right? So that goes up to about 100 plus 800 goes up to about 900, right? So I have this line starts at 100 and goes up to about 900. That's a slope of about 20. So right, it's a kind of my error is relatively low, so it's a pretty nice looking line. Not perfect, right? Because I do have some error, but pretty close to perfect. Now, I think this is like an interesting thing, and this is the kind of stuff that I personally like to play around with. Let's start with exponential smoothing. Now, first off, is exponential smoothing the correct approach? It is not, right? simple exponential smoothing is not the correct approach. Because why? Because I would use simple exponential smoothing in the case where I think my data is roughly flat or horizontal, when I think there is no linear trend. This data, there's an obvious linear trend. So do I think simple exponential smoothing will work well? No, I do not. And so that's what we want to look for in this example. What would it look like if I applied the wrong technique to my data? Look at that. It's interesting. So we'll learn how to generate this ourselves very soon. I'm using something pretty cool called the Time Series Forecasting System, TSFS. I'll teach us how to use it real soon. And it makes these pretty cool graphs. I mean, you know, they're pretty simple looking, but they show pretty clearly what's going on, right? All the asterisks are the actual observations. All the pluses are our predictions. So interestingly, simple exponential smoothing kind of, it chases the data, doesn't it? It does stay close to the data. Where does it really fall apart? It falls apart in terms of its predictions, right? Because simple exponential smoothing is, I'm assuming that the underlying data follows a flat line, so all of my predictions, and that's what's happening after that dotted vertical line, all of my predictions is just a flat line. And of course, right, I can see with my eyeball that that's probably a horrible way to do it. The linear trend is very apparent, and I would assume that that linear trend is going to continue. Simple exponential smoothing, though, is saying, hey, you conjectured a horizontal trend, so I'm just going to predict out that way. So my forecasts are probably pretty crappy, right? Even though it seems like my actual predicted values within the data are all pretty close. Now, do you see anything kind of unusual about that? They're all close, but what's maybe kind of a little bit weird or a little bit interesting? What's a little bit weird or a little bit interesting is that my predictions are always less than the actual values. Isn't that true? That is like sort of like my estimated line is always below what my eyeball would estimate as the true line. The pluses are always below the asterisk. The asterisk is the true data. My pluses are my estimates. This is a great concept question. So I really want you to think about it. And if you're having trouble with it, reach out to me. Why? Why is it that I'm consistently underestimating? Because right? If I look at my if I look at that graph, like what's basically happening? Remember, we said simple exponential smoothing. So what is SAS doing here? What is our model doing? It's basically saying that my estimate, my plus, is always going to be like horizontal, flat, from the previous observation to the previous asterisk, right? And sure enough, if you look, it's pretty close to perfect that every plus is to the right of an asterisk. Right? Because and that's a function of what? It's a function of our model specification. We specified a flat model. So my estimate just goes straight to the right, but the reality is I have linear growth. So instead of going straight to the right, I should be going up to the right. And since I'm going just straight instead of up, I'm consistently underestimating. Do we see that? Now, every time SAS catches that fact, it says, okay, I'm going to go straight, and whoops, I should have gone up. So now I'm going to move up, right? So again, that is pretty cool, right? And that's the fact that exponential smoothing allows for this level to keep changing. So it is kind of like noticing its mistake and constantly fixing it, but then it goes out straight again and makes the mistake again. And then says, whoops, I messed up, and pulls it up, but then goes out to the right and says, whoops, I did it again, and goes up, and just keeps doing that. It keeps underestimating and fixing it, underestimating and fixing it, underestimating and fixing it. So it's like always like a little bit wrong, but it's always correcting that error. Until, of course, we get to the end of our data set, and then now we just project into the future with probably increasingly terrible predictions, right? Hopefully this is an instructive simulated example, and I do want you to think about it. Like what, and again, this is like the kind of stuff that's sometimes fun to play around with, is like well, if I use the wrong technique, what would that look like? How would I catch that? Here is now notice here, like, so this is like some of the output of our information. Probably two important pieces of information there. One is the smoothed level. So that's where I think the level is at time point 36. And that smooth level is 826.44. So when SAS is generating all of its predictions, right? What is SAS predicting for the sales are going to be at time point 37? It's predicting they're 826. What's it predicting them to be at time point 38? Also 826. That level is going to be our predictions. Now that smoothing weight is my alpha. And notice that alpha is about as close to 1 as it could get. And that should be intuitive to us, right? It's basically saying that the level is changing dramatically. It's like, man, this level is constantly changing. And so, right, to accommodate that, I need a very large alpha. Now, let's look at what it would look like if instead of using simple exponential smoothing, I instead used linear exponential smoothing. So this is what? This is the correct approach, right? I look at that data. It obviously has a linear pattern. So fitting a linear smoothing model should work quite well. And look at that, right? Much nicer. It fits that line even better than before. The predictions look reasonable. And correspondingly, look how small that margin of error is, right? The purple lines are the margin of error. It's saying, like, I feel really confident about this. Now, the next slide is going to have our numeric information. It's going to have the level at time 36, the growth rate at time 36, right? We could use those things to generate the predictions. It's also going to have the smoothing constants alpha and gamma. Now, I want you to think. Pause the video, write down your answer. Do you think alpha and gamma are going to be relatively large? Or do you think alpha and gamma are going to be relatively small? Good concept question. If you understand what's happening, you should be able to answer that question. Do you think alpha and gamma are going to be relatively big, or do you think they're going to be relatively small? You were right. They're relatively small, right? My alpha, the smoothing weight for level, is 0.06 out of 1, right? So between 0 and 1, it's much, much closer to 0. and the even smaller is my gamma, the smoothing constant for the growth rate. It's practically zero. Why? Because, right, I simulated the data in a way that the pattern did not change. There is no change in the linear pattern. So I don't really need exponential smoothing. And my exponential smoothing model is sort of detecting that it's not needed by making these smoothing constants very small. The smoothing constant is saying, like, I don't really think that you need to be updating because I don't think that the pattern is really changing over time. Right? The larger those smoothing constants, the more things are changing over time. But I simulated the data in a way that the pattern is always, right, going to be, right, whatever it was, 100 plus 20 times t. And then, right, we also report the smoothed level at time point 36. So if I were to estimate what sales are at time point 36, that would be 819. And then if I wanted to estimate them one time point out, I would add the what they call the smooth trend. That's the growth rate. So that's and again, right, that's about 20, right? So remember the actual slope, we simulated the data, the actual slope was 20. So this came really close to estimating it, right? It said my best guess is 19.975. That's pretty close to the true slope of 20. And so that's basically saying if I want to generate predictions, I just keep adding 20 for every time point out I want to predict for. All right, pretty cool, right? Yeah, I know right now probably what you want to do is pause this and simulate some of your own data and play around with it. That's what I did as a student. I did that, man, Friday night. Oh, so much fun. I would make like a charcuterie board, get like oh man, like some fancy bread, maybe a spread of like meats and cheeses. Maybe I'd go to like the Wegmans Olive Bar. Oh, so nice. Oh, I miss being a student. You have a nice bottle of wine, and I would just simulate like a bunch of data sets, and I would just try like crazy like fitting techniques and just see like how well they work, where they fall apart. Ah, so much fun. I can't recommend it enough. Ah, chef's kiss to simulating data. No, yeah, you might be saying, maybe you stopped the video there and you went to Wegmans and you bought your wine and you bought your charcuterie board and you sat down and you were like wait a minute, how do I actually do the exponential smoothing? Yeah, sorry about that. I guess I should have taught you how to do that. There's a few different ways that we can do it. I'm gonna for now show you how to do it using proc ESM, right? So proc ESM in SAS is proc exponential smoothing. There's actually probably an easier way, which is I showed it to you before. It's called the time series forecasting system. You can use that, and I'll show you how to do that pretty soon. Not just yet though. All right, so here's the general syntax for proc ESM. There's a data equals component. We know what that is. That's just specifying the name of the data set that you want to analyze. There's an out equals. That's if you want to like output some of your information to a data set. There's a print equals. That will tell you like of all the different things that SAS is analyzing, which parts of that you want it to print out to your screen. And I'll show you what the options for that are in just a second. There's a lead equals and a back equals. I'll tell you what those are in just a slide or two. There's an ID statement, which is essentially specifying what your time variable is. And there's a forecast statement, which we use for generating our predictions. Okay. Let's look at each of these in a little bit more detail. So first off, let's look at that print equals option. The default for this is no information, which to me is weird. That is, if you run proc ESM and you don't do that print equals, like nothing's going to show up in your output window. SAS just sort of does it, but doesn't tell you about it. So you want to use that print equals option. And what you can print out onto your screen, you could print out estimates, you could print out forecasts. performance statistics, summaries, and all. And you can play around with that to see like what is in each of these little subcategories. And if you wanted just like to pick and choose like 2 or 3 of these things, you can use parentheses. So if you wanted to output estimates, forecasts, and performance, you could put all 3 of those inside parentheses. Performance statistics is something we'll talk about a little bit later in the class. But that's kind of like model validation. Like in 512, we talked about how you might hold out data, and then you could build your model and test it on the data that you held out. That's basically what the performance statistics is doing. The lead equals statement basically tells SAS how many time points into the future you want to predict. And the back equals statement tells SAS how many time points you want to hold out. And again, like I implied, this is to kind of help you validate your model. We'll talk more about this down the road, but based on what we did in 512, you should have at least a little bit of an intuitive idea of how it works. In terms of the ID statement, the interval equal is mandatory if you use the ID statement. So if you use the ID statement, you're saying that there's some sort of seasonality. It's saying that your time variable is has some sort of formatting to it, and then you have to tell SAS what that is, right? Is it interval equals year, semi-year, quarter? These are all the date formats that you learned in 511. Now, if you don't want to mess around with that formatting, it can be a little bit finicky. If you don't want to play around with the formatting, you could actually omit the ID statement. If you do that, SAS will just use observation numbers, right? So it'll just say your first observation is time point 1, and your second observation is time point 2. And if you wanted to still do seasonality, then you can just put seasonality equals L in the proc ESM line. So like if you had monthly data, you don't actually have to like format it in a monthly format. You could just like use observation numbers and put seasonality equals 12. That's the way I typically do it, because again, I don't know, probably someone who does this more regularly is probably a little bit better at the whole date formatting. I admit I kind of struggle with it, and so I try to avoid it whenever I can. You may or may not feel the same way. The model equals statement specifies which exponential smoothing model that we want to do. The default is simple exponential smoothing. But we could also do the linear that we talked about, the damp trend. We could do winters, which is like a multiplicative seasonal model. We could do additive winters, which is the additive seasonal model. We could also do something, I didn't talk about it. There's something called double exponential smoothing. I think it's talked about in our textbook. I don't see it used very often in real life, so I didn't talk about it in our lecture. But it's like a linear model, but it doesn't work as well as like the linear specification. So I'm not really sure why you'd use it. It only uses one smoothing constant, so it's computationally simpler. But in this day and age, we don't need that computational simplicity anymore. So I put it there for completeness. It is in your textbook if you want to look at it in a little bit more detail. But I wouldn't recommend using that double exponential smoothing. Okay. So here is right, here's an example kind of pulling it all together. This is exponential smoothing. I'm using it on I think this is a fictitious data set from our textbook, and I'll make it available on D2L if it's not already. I think it looks at 10 years of paper towel sales, monthly sales. So 10 years is 120 observations. And right, I can this is like the code proc ESM, specify my data set. back equals 55. So I'm saying hold out 55 observations. That's more than you would typically want to hold out. I'll show you why I'm doing that in a second. I'm doing that for pedagogical purposes. Lead equals 67. So it's an arbitrary number. I just wanted to kind of project it out into the future quite a bit. Print equals estimates. I wanted to take a look at our estimates. And then you can actually do a plot statement with ODS graphics, which looks pretty nice. And we'll look at that plot in a second. And here I do linear exponential smoothing. So model equals linear. For the record, when I look at this data, we'll see that linear is not the best approach. And that's part of what I wanted to illustrate with this example. Okay. So here's what proc ESM looks like. It shows me the exponential smoothing weights. The level weight is quite high. It's saying that the level is changing dramatically. It's claiming that the trend, the growth rate, is not changing. All right. Sometimes, like when it's just like the underlying pattern is going a lot, SAS, the volatility can be represented in a couple ways. The fact that level is so large is expressing that there's a lot of volatility in our data, despite the fact that SAS thinks that there's a quote stable growth rate going on. All right, so when you run that data, you got to look in your results window. We're used to that. We use plenty of ODS at this point. And so here's my ODS graphics. And so right here's the plot of like the paper towels. I don't know. Again, I think it is kind of real life looking. It's from our textbook, which normally does these contrived examples. I don't know. We see like paper towel sales look kind of largely stable, maybe trending downward a little bit. Then there's the I'm sure you've all heard about the great paper towel crash of 2019. I guess I don't know. Maybe. Yeah, I don't know, maybe toilet paper, toilet paper crash of the pandemic. Maybe this is like availability of toilet paper, and then it crashed down low, and then kind of started to pick back up. Now, right, this is like a good example of like how you want to be like a little bit careful using exponential smoothing. Because what's happening? Like what's happening is like SAS is like seeing that there's a lot of noise in that data, right? This is kind of an unusual looking data set. Like what is that? It looks like it is a combination of kind of like sometimes going flat and then sometimes decreasing and then increasing and then going flat. It's like a combination, right? It's a combination of no trend and linear trend. And trying to fit either of those models, SAS is going to detect a lot of volatility. Since it detects a lot of volatility, it's putting a lot of weight on recent observations. And so what happens? It's putting so much weight on recent observations that when it hits like that end point, that dotted line, it detects like a very small linear decrease and it just goes with it. Even though like that linear decrease doesn't really fit like where the data is going, it doesn't fit like what's been going on in the data. In this particular example, it's kind of just fitting noise. And we can see it generates some predictions that like are pretty terrible given that we know the data, right? This is the beauty of using that back equals statement, right? I held out 55 observations, right? Doing that's really nice because it basically shows my predictions and I can line those predictions up with what actually happened. In this case, I could see that my predictions are terrible, right? So a little bit, so what's going on with this example? This example is one, it's showing us the proc ESM code and how to use it. So there's that. It's also an example, like a cautionary tale, that exponential smoothing, it can work really well, but with noisy data, if we don't use it appropriately, it can work pretty poorly as well. How would I analyze a data set like this? Well, one, I said in a previous slide that if I have a situation where it's kind of like piecewise no trend and piecewise linear trend, that I would use a dampened trend model rather than a linear trend model. So I probably maybe should have used the dampened trend model. A dampened trend model would probably fit the data better. In fact, I'll give you that data set. You can play around with it yourself and try fitting the dampened trend model and see how it works. We could also, of course, try a different technique, right? We could try something other than exponential smoothing. And so there are techniques that maybe work a little bit better in situations like this. And of course, that's what we're going to be learning next week. So this example and the fact that exponential smoothing maybe doesn't work so well on this data set is a nice kind of motivation for the new type of technique called ARIMA modeling that we're going to start talking about next week.